Switch to. Okay. So, does anyone have questions on stuff that was taught in last week? I know there were a few issues with installation. Sriram had some issues. Did you manage to fix it, Sriram? Are you around, Sriram? Not yet. Okay. So, in the worst case, right, what I'll do is you can start. So two things, right? You can start working on the assignment with that online editor. But what I will try to do is to set you up with the Emacs SpaceMax environment in a virtual box. Maybe I'll ask one of my PAs to do it for you. So we'll just package it up. Um, there are ways around it. Maybe that's the easiest one. I don't want you to be stuck on um, these setting up issues and get on with interesting work on the implementation. But anyway, these are things that you have to end up doing anyway if you work with the research software. So my suggestion is to actually use Vimala's time this evening, see whether if it's a simple thing that can be fixed. If not, send me a message. I'll try to package something up. I'll ask either Vimala or Shira to package something up. Anyway, so with that, let's get started. So what we have seen so far in the previous few classes is program verification with F-star, right? And we saw how uh, the power of SMT solvers makes a lot of the proofs go through very easily, right? And integer theories and um, many things that we took for that were really painful, tedious in Cork were easy, but there was also other things like actually applying induction and seeing what is true about the environment that was difficult. So there is this automation that is sitting within F-star, right, which is sort of helping you. Um, and so far, what we've seen is a lot of the things that we've seen in Cork is very explicit. But Cork has a very expressive way of doing automation. You've already seen it with expressive tactics like linear arithmetic and so on. But I want you to sort of develop an intuition there. So we will jump back to Cork for the next part of the course, because in order to teach about further effects in F-star, we need more programming languages foundations, which we will see, which we will develop in the next few weeks, right? Um, so this lecture is going to be on, say, a digression, right? Let's not, this is not actually introducing a particular concept, or it is not actually um, teaching you something new. So it is sort of a digression where we sort of see this unique way of reasoning about programs within Cork. So think of this as not a new PL topic, but a new way of doing automation. And the goal here is to sort of see what sort of automation can we actually do within Cork and how the automation actually helps us. And there is some foundational ideas within this lecture. This lecture itself is called logic programming. Essentially, what we studied in CS3100 prologue, right, where we did logic programming, that sort of underlies some of the automation techniques that is being used within Cork for writing expressive tactics, and we will develop an intuition for expressing some of that, right? So this doesn't neatly fit the path that we are going. It's sort of a digression, but we will introduce some ideas which we'll come back to later in the next lectures. So again, we are switching to Cork, our familiar setup, and we are using the frap library. And this set implicit arguments is sort of just there. It just means that consider any unsaid arguments to be implicit, so that goes through. So we are going to do logic programming. For those who have not gone through the prologue part of the course, don't be alarmed. You don't need to know prologue for appreciating what is going on here. There is if you sort of paid a little bit of attention, there is a lot of interesting overlap between what we had done in the GADT lecture, where we had explicit proofs, and how we've done prologue. Some of that will become much more apparent in this lecture, and that's the point of this lecture. You don't need to know much of anything about prologue for doing this, but knowing this, you might find some common ideas that are in practice. Okay, so let's start with a very simple example. Let's recall the definition of plus in the standard library. So here is the definition of plus. It's a fixed point, right? And if you take n and m, again, um, natural numbers in Coq are encoded as inductive types with O and S, right? So the addition itself is implemented as a recursive function on n and m. If n is 0, then it is m. If n is non-zero, then you add the tail n minus 1 to m. I mean, this eventually terminates, and then you add an s around it. And this is very similar to this sort of isomorphic to how append function looks, right? We have a representation which has so many s's, and then we are creating a representation which has um, as many s's as the sum of the two, right? So this is sort of the functional way of encoding natural numbers. There is also a logical way of encoding it. This functional way is a recursive definition, right? We recursively call add. This fix is again a keyword in Coq. I don't think we've seen this. This is sort of standing in for letrec, right? Whenever we want to use sort of a letrec, you can use a fix, and we name the function so we can call it again. So this recursive definition, we call it the FP style, right? We also have a logical style of defining the same um, property of additions, right? A subset of the property of additions. So here is the inductive definition of what we are expressing in terms of capturing the relation between three natural numbers that are related by additions. Again, this is very similar to what we had seen in the GADT lecture. So we are going to write a relation that captures the relationship between three natural numbers, right? And we call this relation plus r. There are two ways in which we can relate these natural numbers. First is plus o, which says that for all natural numbers m, right? If you add 0 to m, you get the natural number m. I mean, this basically says 0 plus m is m, right? Which is sort of analogous to the base case here, right? I'm sort of closely following analogy because I want you to appreciate this, right? And then we also have a rule for plus s, which says given three natural numbers NMR, which are related by this plus relation, which essentially means n plus m is r, then we can also say that n plus 1 plus m is r plus 1, right? And this is sort of capturing this relation because the first one is you have to read it backwards as you do with logic programming, but essentially this is non-zero, this is non-zero here, right? And you get s added to the result, you get s added to the result, and the way you sort of look at it is you sort of look at it backwards, right? If you can sort of show that if you want to show that n plus 1 plus m equals r plus 1, it is okay to show that n plus m is r. So these two definitions, although they look very different, one is written as a recursive function, another it is written as a inductive relation, just a data type definition. They are both related. They are both sort of isomorphic in if you look at it, if you sort of squint and see the relationship between them. So firstly, right, so does anyone have question on the definition itself, what this definition says? Okay, so we are not saying much here, right? I am just capturing these as facts. 0 plus m is m. If you can show that n plus m is r, then n plus 1 plus m is r plus 1. That is all we are capturing. That is, we capture that as inductive relations, right? And recall that Cock will automatically derive induction principle for any inductive definitions, right? For a list, you have a list induction principle. It says that if you want to prove any property on a list, you first show the base case, you show the inductive case, right? This goes up to here. And then once you have both, then that property holds on all of the lists, right? And similarly, you have an induction principle for the definition, the inductive definition here. It is perhaps useful to look at the structure a little bit closely. Suppose you want to prove some properties that relates three integers, right? Let's say that is what I want to do. If you show that this property holds on the relation P0mm, right, which is sort of analogous to the base case here. We have a plus R here, but if you can show that the property holds on P0mm, and then assuming that plus R NMR holds, the property that you want to show P NMR also holds, then if you can then show that P of n plus 1 m r plus 1 holds, again this is sort of analogous to this one. So this is the base case, this is the inductive case. So what does this buy us? Then in order to prove this arbitrary property that relates three integers, you can use the fact that these three integers n, n0 and n1 are related by plus r. So essentially the high level way to look at this one, this induction principle, is that if I want to prove arbitrary properties about three integers, this property P on three arbitrary integers, n, n0 and n1, when can I use the fact that these three integers are related by plus r, right? These are sort of expressing some facts, right? When can I use those facts? You first show that the fact holds on the base case. You then show that the fact holds on the inductive case. If you can show that, then you can use the properties that you define here. You can sort of take these as axioms, right? These are not like these are what you define. So if you define something wrong here, that is that would be a incorrect axiom with respect to what natural numbers mean. But really, if you want to use this, you need to show that the property holds on the base case and the property holds on the inductive case, right? And then you can sort of use this property, these axioms that you've defined on natural numbers here in order to prove arbitrary properties, right? So that is the induction principle. So you can apply induction on this inductive type as well. This is quite powerful. Firstly, right, the point is that so we defined a recursive definition, a functional version of plus, right? And we defined the logical style, and both are related. So whenever a property on one of this holds, the other one also holds. Let's actually relate them together, right? Intuitively, a fact plus r NMR, which means that n plus m is r, holds whenever plus n plus m, if n plus m is equal to r. I mean, this is the intuitive definition, but it is we have to explicitly express it because these two are sort of two different things as far as Coq is concerned. So we can actually prove it very easily. All we are saying is that plus r nm n plus m holds. So we are connecting the logical definition with the functional one. This plus here is actually going to appeal to this real plus, which is the recursive definition, right? So we are sort of relating the logical definition with the recursive one. So we are making this connection, right? We are sort of saying this logical form only holds whenever this functional form holds, which is what we intuitively expect, right? The proof itself is simple, but I want to go through this because I'm going to introduce something new. So again, we do induction on n and then we do simplification. So we are left with two sub goals, right? The first goal says that show me that plus r 0 holds. So the way to read this is that here is a, so we don't, so the one day interesting assumption that we have is that m is a natural number. We don't have anything else. So this has to, if you have to show that this is true, this has to be a fact that is like basically there, right? It's just a value that is just there. And we know that is a value that is available because if you sort of look at this plus so constructor, you can sort of look at that as evidence for all natural numbers m plus r 0 holes. Again, use the Curry-Howard correspondence, right? So this is the value, that is the proof, and this is the type, that is the theorem. So in order to prove this theorem, it is you can appeal to this particular constructor that you can give as evidence for that. So so constructor is a tactic, right? That just picks one of the constructor that applies in order to prove the theorem. So because we are directly giving plus so as the evidence, you can just say constructor. So it applies the that particular constructor which can unify with that. It applies that in order in which the constructors are defined. Because plus so appears first, that particular thing goes through. So that whole proof is satisfied thanks to the fact that we have a value whose type is the proof for the thing that we want to prove. Right? I believe I can also use exact plus so. No. Oh, you need to instantiate the term. Yeah, I can't use exact plus so because there is a for all. But anyway, constructor does the instantiation as well. Maybe I can use, one second, let me not give up. Because I know that is a function and I have m in context, maybe I can use this. Yeah. So do you see what is happening here? So when I just used, so exact is what we had seen for when we studied the logical foundations lecture, right? We used exact type as a proof for true. So I know that plus so is a constructor and it's quantified with the for all. So for all is a function, right? So I'm just applying plus so to m to get the value, which is exactly this one. And I'm just saying exactly that one is what you want to do. And that goes through. You can also do constructor, right? That is also the same thing. Constructor automatically applies the matching one. I believe I can also do apply plus so. Yeah, that also makes it go through. So what I'm doing is I'm using plus so as a proof, right? The way you have to read this is that true implies this one, right? Given any formula, true implies this formula. I'm just applying that function so that I'll be left with true, which goes through. So apply plus so um, solves this requirement, right? So those are three ways of doing it. So you can do constructor, you can do apply, but you can also do exact. I just add these in comments so that they are there. Exact plus. Any questions on this? How this goes through? But constructor automatically picks the right constructor and applies it. I mean, the first constructor that matches it. Okay, so that is the first one. For the second one, we have to do the same idea, right? So I want to prove that plus r s plus 1 m s of n plus m holds. And the induction hypothesis is actually on n plus m. So this s is gone, right? And this proof plus s is what I want, because you can read this as a theorem, right? For which, in order to show this, I can show this one, right? Which is what the logical reading of this particular type is. So by applying that constructor here, the second case, the requirement, the actual goal changes to the antecedent, right? The antecedent is plus n m, r is here n plus m, and that is just induction hypothesis. So you can just apply the induction hypothesis here, and that goes. So, I mean, we've done a very simple thing, right? All we've done is we've sort of related the logical definition to the intuitive definition of what we expect from the natural numbers, which is that plus r nm r holds if only r is n plus n. That is all we've done. Questions on this one before we proceed? No questions. Okay. So let's maybe speed things up a little bit. So the thing is, if you look at this one, it's very, very mechanical, right? We've sort of taken all of the constructors of the plus R as a possible things to try in order to prove properties on plus R, right? If you have a goal which introduces a plus R, then you can take these constructors as possible proofs of making progress. So one way to extend the functionality of Coq, right, is by adding hints. So the thing that I try here is that I say that all of the constructors of plus R, consider them as hints for this auto rule. So recall that we've seen auto much earlier. Automatically discharges proof by searching through the possible um, proof roots, right? And here I'm saying, because this is a new constructor, I'm explicitly saying consider those constructors as part of the proof search database, right? And you'll see a complaint which says that I'm adding rules to the global database. You can ignore this error for now. It just says that we are typically adding proof search rules to global database means that you're polluting the entire environment. And the recent version of Coq says that you should always give a specific scope so that the proof search is not too wide, and this auto rule does not end up with too many things to do and gives up quite quickly. But you can ignore that for now. Okay, let's do the same thing again now with auto, right? All we've done is construct a constructor, apply induction hypothesis. So here is the same theorem, right? I induct n, simplify, and then apply auto, right? It automatically goes through now. We are not, we don't have to sort of explicitly appeal to the individual constructors. Actually, we are not, right? We are just working through each of the constructors. Yeah, so here is the same theorem. I just want to do this just to show you other ways of doing induction. So here I just substituted for r n plus m. And here is the same theorem expressed in a different way. It just says that for all natural numbers NMR, if plus r NMR holds, then r must be equal to n plus m, which is the same as this one. So here is the actual theorem. Now we are going to prove it. So one thing is that Coq allows induction on any inductive type, right? So we've applied induction on list before, we've applied induction on trees before, we've done induction on natural numbers because they are also inductive types. Similarly, this plus r fact, right, is also an inductive type. So this thing is also an inductive type. So you can apply induction on plus r, right? What does that mean? It basically means that you have to show we have derived an induction principle for plus r, right? So you can apply this induction principle in order to induct over the goals that are here. So and the way you do that is you actually call induct on one. And what this means is that Coq will perform induction on the first hypothesis. So in when you have P implies Q, we are actually inducting on this P, and we are able to induct on this because this is an inductive type, right? And the thing to note here is you'll have two subgoals which are precisely match the shape of the constructors, the type of the constructors that we have. So why do we, when we induct, why do we get two subgoals? We get two subgoals because we have two constructors, right? And the first subgoal, before induction, observe that the proof obligation is assuming plus r nm are holes, you have to show r equals n plus m. The first of the constructors, right, says that 0 plus m equals m. So substitute 0 for n, m for m, m for r. So assuming this, you have to show this. So I have to show that m equals 0 plus m, right? And that is what I will end up with when I do induction. So assuming that the base case, I have to show m equals 0 plus m. And this goes through with linear arithmetic. But I mean, just to show that it goes through, I'll write it here. So I can also use ring. Yeah, that goes through. So one useful technique for proof organization is that when you have multiple subgoals, you can choose the subgoal you want to attack first. So, so one way of doing that is having this, right? So this is going to give you focus. You can always do an admit, which admits the subgoal. It highlights that with yellow. This admit is similar to the admit that we've seen in F star. And then focus on the second subgoal to prove, and then you can go back and prove the first subgoal. But Coq also allows you to do it differently. So when I have multiple subgoals, I can just give a number, right? N colon open braces. Actually, n colon will be sufficient. So if I do 2 colon, uh, 2 colon this one. So observe that I am sort of focusing on the second subgoal now. So I can choose to prove the second one first, right? So I'm choosing to prove the second one first. The first one is still yet to be proven. So we will come back to that. And how do we prove this? You can simplify this one automatically, right? So r equals n plus m. So if you simplify, let's do simplification. I mean, the proof itself is very simple. So if you simplify, you get s of r equals s of n plus m. And of course, you can do f equal, right? You get r equals n plus m, and then assumption makes it go through, right? And instead of doing all of this very explicitly, you can just call linear arithmetic, which does all of this wholesale thing for you. So if you do this, then the second one is done. Okay, that's done. Because we chose the second one to prove first, we are still left with the first sub goal, which is this one, right? And we can make that go through with linear arithmetic as well. So the point of doing this again here is that just to show that when you have complex subgoals, you can choose the subgoals to focus on. So if you have n subgoals, you can choose one of those n to focus on first, and then for the rest of it, you have to keep. You can keep applying this whenever you have multiple subgoals. Any questions on this one?
So if we had 3 subgoals and we sort of choose to focus on the second subgoal first, like will we, after we prove the second subgoal, will we go to first subgoal and third?
Yeah, I think you will be left with first and third. Then you'll end up with 2, and if you choose the second one, it will be the third one from the original list.
Okay.
So yeah. So it's a useful trick. Sometimes when you see it, you'll see that you have one subgoal which is quite difficult. You actually want to attack other ones and come back. So this is quite useful trick to do. And the trick that I actually prefer is this trick, right? I just admit one, and then I prove the second one, so I can do linear arithmetic. So and it says that no more subgoal, but there are some subgoals you gave up, right? The first one I gave up, so there is excuse me. So there is some work that needs to be done. So I go back and finish that. So any other questions on this one? Excuse me. Okay. So let's keep moving. So again, there is this duality, right? There is this functional way of looking things. There is the logical way of looking things. Equalities are easy to prove in the functional way because you can just evaluate, right? You can just go through the program and evaluate. So I'm proving 4 plus 3 equals 7. Reflexivity makes it go through because reflexivity also does the simplification, right? Yeah, EQRFL is the proof for it. EQRFL does the simplification as well. But if you sort of try to prove the same thing with logical proofs, right? You have to construct this interesting proof. Um, but it's a bit mechanical, but you can sort of, I will go through it step by step to show you how mechanical is it, and then develop the intuition for how you can automate it. So let's try a simple-minded approach, right? We just apply the first constructor. There are for plus r, I'm proving plus r 437, which means I'm essentially proving the same thing as here, 4 plus 3 is 7. The approach I'm going to adopt is I'm going to try the first constructor. If it fails, I'm going to try the second constructor, and I'm going to. There are only two ways of proving it, right? At the end of the day, I mean, it has to be a combination of this. Let me try a very simplistic approach where I first apply the first one. If it fails, apply the second one. Of course, I prefix this with fail here just for illustration. So the point of this fail is that in Coq you can add explicit fail to any. That's a tactical. Right? You can prefix it to any tactic to say if it fails, ignore the failure. Right? Um, yeah. So I am first applying plus O. Plus O will not work here, right? Because I cannot unify this because in order to unify this term with plus R, the first one has to be 0, right? If you go back to the definition of plus O, right? Uh, this, if you apply plus O, the first term has to be 0. The first term is not 0. That doesn't unify. So what you have to do is to try the other one. Let's apply plus S. So we reduce one step, thanks to the fact that these are actually unifiable now. For people who've done Prolog, um, think about SLD resolution, right? This is exactly how SLD resolution used to work. You apply the first one, or else you apply the second one, and then you have a bunch of other sub goals which you sort of go ahead and prove, right? I tried the first one that failed, and then I tried the second one that had a precondition, right? Um, that had a precondition here, which is what I am left to prove now. Again, SLD resolution does the same thing, right? Again, try the first one, it fails, right? Try the second one, goes through. Try the first one, fails. Try the second one, goes through. First one fails, second one goes through. Finally, you are done with, you're at plus R 033. And at this point, the plus O satisfies, right? And there are no, that's a fact. I mean, to use Prolog term, that's a fact. That's not a rule. Um, so that's a fact. So this fact is true. So the fact makes the thing, makes the proof go through. Observe that this is very mechanical, right? Applying plus O plus S plus O plus S. This is what auto does essentially. So if you, so here is another command. Again, I introduced lots of commands. None of many of these are not important, right? And this is one unimportant command just for edification purposes, right? Just so that I can tell you how these things work. When you do restart, what you do is you build up a proof state up to this point, right? You started a proof, you build up a proof state. Restart just throws away that proof state and starts from scratch. So even though I proved it here, when I do a restart, I have to, I'm essentially saying throw away the proof, I'm going to start from scratch. So the way of mechanically doing this is what auto does internally. So if you do auto, it automatically goes through and says auto has actually completed it. You can, so one thing you can do is you can do info auto, which tells you what are the successful rules that it has applied. Observe that it has done simplification, apply plus S, right? Plus S. There is one more plus S, there is one more plus S, and similarly there are two more. There are two more pluses and plus 0, two more pluses and plus 0. This is what auto has done internally. These are the successful rules. If you actually debug auto, right? Auto does a lot of things, right? It tries assumption, it fails. It tries introduction, it fails. It tries to apply plus O here, right? And it fails. This corresponds to this failure here, right? And auto tried that particular constructor because we explicitly suggested these constructors as hints for auto, right? And that is why it is trying those, and it tries pluses that is successful, so it makes progress, and then it tries assumption, it tries introduction, it fails. Auto is like very simple minded. It goes on and tries a few things, and if it can make progress, it can make progress. And one thing to remember is that proof search is infinite, right? If you apply the wrong way to, if there are two equivalent ways to go towards a proof, and because the because both SLT resolution and the way auto works is apply the rules from top to bottom. If you go down the wrong route, you can go down infinite search trees. So auto is sort of parameterized by the maximum depth. So the depth is sort of 1 here, right? And depth increases to 2. Here we are able to solve with depth 5, right? And by default, auto has a depth which is explore the proof tree up until depth of 5. It doesn't explore further. So let's see an example where a simple auto does not make it go through. So earlier we proved 4 plus 3 equals 7. Now we are proving 5 plus 3 equals 8, right? If you just do auto, this time auto doesn't make progress, right? Auto turns green because auto just ignores the errors, but the proof isn't complete because auto only tried until depth of 5. You actually have to try until depth of 6 in order for this proof to go through. So if you do auto with 6, it tries until depth of 6, that proof goes through. You can find what is happening with this depth here. So 1, 2, 3, 4, 5, 6. You needed to recurse 6 deep, and info auto 6 was successful. But if you do, yeah, so this also shows the failed steps. The same thing, right? So 1, 2, 3, 4, 5, 6. You have to explore until 6 deep. So what are we doing, right? Essentially, what we are doing is SLD resolution and prologue style search for proofs. And for those who don't know prologue, right? Prologue itself is sort of builds on these very simple ideas. So you have a set of facts and rules, just like what we have for plus R. There is plus O and plus S. And you have a very simple-minded strategy which applies these rules one at a time. And the idea is that certain rules unify. So an example of unification is here, right? When we tried to apply plus O here, it failed to unify because the expectation was that the first argument was 0. The first argument is a 4 here. It failed to unify. So you try the next one. Here it unified, right? For this it unified, and then you sort of go towards proving whatever the goals that were in the body, essentially, right? And that one fundamental idea of logic programming is unification. The other fundamental idea is you might go down a path in your proof search, right? But you might hit a dead end. You tried, there were several options. At every point, all of the constructors are applicable. Few of those are unifiable, right? And if you go down one path, you might go down a path where a particular step is not able to make progress. You have to backtrack to a point where the second option is applicable, right? And let's look at both of these in action, right? When you define logic programming, this is basically how we people define logic programming, backtracking and unification. These are also how proof automation and COG works, right? So we are going to do a simple example, very silly example. So we are going to, the point here is that I want to show where logical thinking actually makes a useful addition to the language rather than this functional thinking. Um, so yeah, so here is the existential intro rule. Okay, so here is, what does it say? It says what we intuitively understand about existential introduction, which is that if you have a property that holds on A, right? A holds P holds on A, right? And we have a property P, right, which is a to that prop. that property is some property, and we have this x which is of some a, and if p of x holds, then you can say that there exists some y on which p of y holds. And of course, it is sort of a very simple reading forwards, right? So we know that there is an x on which p holds. So of course, it must be the case that there exists an y which p of y holds. If you read it backwards, it is more interesting, right? So in order to show that there exists a y such that p of y holds, I have to find an x on which that p holds, right? So this is what we are going to do. So here is an example, right? So here is one way of writing exists. This is the first time we are seeing exists, I believe. So far we've used for all everywhere. So we are writing there exists an x for which x plus 3 is 7, right? And for for explanatory purposes, let us assume that I have minimal understanding of arithmetic. I know that the answer is 4, but let's start doing very simple-minded way of proving things, right? Let me start at 0. Let me say, oh, I'll just plug in 0 for this one, and let me see if that goes through. So I'm going to apply existential introduction, right? The rule that we just saw here. I'm going to fill in 0 for x, right? Let me fill in 0 for x. And let me try to make it go through with reflexivity. Of course, this doesn't go through with reflexivity because 3 is not equal to 7. So this fails. So eventually you can sort of you tried 0, you failed. So you go back, you can try 1, you go back, you can try 2, you can go back, you can try 3, you can go back, you can try 4 finally, right? And when you finally try 4, right, we are restarting here, we are going all the way back to the start of the proof. Um, so when you try 4, it goes through, obviously, right? So 4 plus 3 is 7, reflexivity go through. So this is fairly tame. So in this example, every time we failed, we rolled back all the way up. But you can imagine complex program where you made progress somewhere, and then you only roll back a certain depth, right? So this sort of proof search is very complicated. And and in Prolog, just to feed some ideas to people who taken Prolog, these are essentially choice points, right? When you have multiple choices at a certain place where you can make progress, you go down one path, maybe you fail there, you come back, and then if there is another choice there, you go down that other path as well. This is essentially how we are going to try to prove it in the logical version, right? So I've just written the same existential quantifier here, right? I'm proving x3 7. So I'm trying to prove in the logical formulation x plus 3 is 7, right? Um, we can try quantifier instantiation as above, but because this is we are in this logical world, right? We can introduce unification variables. We can introduce unknown variables for this place, which we can resolve later from other goals. So these unknown variables are similar to variables in Prolog, right? I'm just going to introduce a placeholder for this variable, and then I will try to keep proving. Eventually, this placeholder will be unified with some concrete value, and that concrete value will be substituted everywhere, right? That is precisely the reason that the reasoning that we are going to use here. And the way you do this placeholder introduction is by using this rule called apply, right? So when we did apply, I said apply existential introduction with 4, where I'm saying I'm going to use this rule. I'm going to introduce 4 for this whole, right? But there is this variant of this apply rule called apply, where wherever there are these unknown variables, you actually introduce a placeholder. You introduce a unification variable, question mark x. So the way to read this is that there exists some variable x, right, where x plus 3 is equal 7. I have to prove it. And when this variable gets unified to a concrete value at some point, everywhere in all of the goals where this same variable appears, it will be sort of substituted. So we've introduced this. Let's actually proceed. Now we can actually proceed by applying the same reasoning as above, which is that you can just um, try the constructor step by step, right? So I'm not showing the fail steps. You can just apply plus 0, that will fail. You can apply plus s, right? Oh, you have to find this some n variable. I don't know what that n variable is. You can apply this pluses again, apply pluses again, pluses again. There is this n variable which needs to be filled. Eventually this n will be filled with 0, right? And then the goal goes through, and eventually that x has been filled with 4, right? So you can see that by um, um, by actually introspecting on this auto rule does not include e apply as part of the things that it tries. So if you have an existential quantifier and you apply auto, you won't make progress, right? You get stuck. But there is e auto rule. So there is this rule called e auto, and all it does is it also additionally includes this existential quantifier instantiation. So if you apply e auto, observe that it has first done existential quantifier instantiation, and it has successfully applied 4 instances of s plus s and then plus o, and the proof has gone through. So if you print out the proof, you will see that it has found the proof, the actual proof where the x has been filled with 4, right? It does existential introduction for this thing with 4. Um, and thanks to this unification, right? This unification variable that we've introduced, we were able to find the value that needs to be satisfied for this existential variable that appeared here, right? So this is an advantage of doing logical reasoning. So uh, I mean, this seems very simple, but um, this sort of underlies the first example where logical proof search is much more powerful than um, doing proofs in a functional programming world. Okay, so um, at its heart, right? Again, this is something that we've already seen in logic programming. At its heart, if you look at a functional program, it takes an input and returns an output. But a logic program does not have an input and output, right? It is just a database of facts. So you can run it in forward direction, but also in backward direction. And that is what we are using in order to deduce the value for which this particular existential variable, um, I mean, deduce the value for this x, which satisfies this fact, right? We are basically running the program backwards from the end of the program. This is the property that we want. We're going backwards to see what the value of the variable should be. And of course, the same works for any other unknown value. So if you think about this as a functional program, right? The question that I'm asking here is, what is the value of x such that 4 plus x is 7, right? And if you do e auto, it automatically finds the proof for you. And if you print the proof for, I mean, this is uninteresting, but essentially you can print the proof for this value and then see that the value that is filled is 3, right? It has solved it for you, essentially by running the program backwards. I'll stop here, actually. Can we prove x plus y equals to? Good question. Let's try that. I think this will get stuck. This is the syntax. Okay. Oh, fine. Okay, so it actually went through. Yeah. So, and funnily enough, it instantiated that with 0 and 7, right? Uh, so 0 and 7 is 7. Um, let's make it stronger. Uh, x not equal to 0. Does that work? Yeah. And now you can see what the values it found. Uh, it found 1 and 6 as the values, right? So basically this is constraint solving, right? And this is a very limited form of constraint solving. Again, for Prolog people, um, we know that the language that we have uh, is a definite clause language, right? It's not full first order logic, so we cannot solve arbitrarily complex first order logic proofs. These are like a very limited set of things that we can do, and we can do that quite effectively. So this is not like integer theories. This is not like SMT solving, but um, we are using logic programming as a solver here in order to solve interesting queries. Yeah, I mean, you can arbitrarily say that, uh, yeah, so y is not equal to, say, 6. And it finds a proof. Oh, okay. So that fails. Is that due to the depth? Yeah, okay. So that's basically due to the depth. So it found a value, right? 2 and 5. Anyway, we are seeing very simple examples of this, but in the future lectures we will see. Um, in the next lecture we will see more interesting ways of applying this. But this sort of reasoning will also be quite useful in the upcoming lectures, where we have to reason about more complicated programs, essentially. When we have to define infinite systems, we cannot define them as recursive functions, because recursive functions on infinite systems will not be allowed by Coq, right? Because it expects everything to terminate. We will define them as inductives, and then we will use the rich automation technique that we have in order to make the proofs go through automatically. And that's the reason why we are sort of building up this lecture. That's why this is a digression. But anyway, so there is more stuff in this lecture which we will cover in the next class. And then we will jump to transition systems, where we will start using these ideas in practice. Any more questions on this one? Okay, if not, I'll stop here. We will catch up tomorrow. Thank you.